Hello, everyone. My name is Escamilla Torres, and I'm going to talk to you about my PhD work. It's called Reconstructing Dark Energy, and I'm working in collaboration with my supervisor, Jose Alberto Vasquez, with Eleonora de Valentino, and with Osgura Carso. So, as a brief introduction, let me talk to you about the standard model of cosmology, ΛCDM. This model is considered the standard one because it explains most observations and most phenomena. But as I'm sure we all know, as more data becomes more abundant and more precise, we are starting to see problems with the standard model ΛCDM, such as its problems at small scales. We also have the famous Hubble and sigma tensions. We also have the coincidence problems, the fine-tuning problem, and one of the most important ones is that we don't really know what is the dark energy and the dark matter, which is the dark sector of this model. Here we have a representation of the cosmological tension in the H0 parameter, a comparison between early time data and late time data. We have at worst 6.1 sigma tension between the late time data and early time data. So this tension is one of the biggest problems in cosmology right now. And we can try to solve this problem in basically two ways. We can either say that there's something wrong with the data. If we take this approach, we need to start making assumptions about systematic errors in the data, or also trying to wait for better and bigger data sets to come to finish in the service. Or we can take the other approach, which is to suppose that our model is wrong, in this case ΛCDM, and try to propose alternatives to it. One of the alternatives that we're going to focus in this work is the named reconstructions. They can be basically classified in three types. They can be parametric, non-parametric, or model independent. So what are the parametric reconstructions? Basically, a parametric reconstruction is when you propose a functional form or a parametrization. It can be either physically motivated or it can be completely phenomenological. For example, two of the most popular ones are the ΛCDM, in which the equation of state is only a constant, or the CPL parametrization. You need to determine the values of the parameters of each parametrization by using cosmological observations and data. So we are assuming the data is basically okay. And they can be also used to study some kind of behavior, such as oscillations or exponential growth or whatever you wish to propose. Here we have a list of examples of these parametrizations. We have like a Taylor series. We have also cosines. We have logarithms. You can propose basically any function you want and see how it behaves with the data. Then we have the other side of the coin, which are the non-parametric reconstructions. These reconstructions do not assume a specific functional form or a parametric model. They typically rely on statistical, computational, or numerical tools to analyze data and see how the data prefers a quantity to behave. For example, here we have a Gaussian process, which is a popular reconstruction. Here is being used with cosmic chronometers data to reconstruct the whole parameter and see how it compares with ΛCDM data. We also have other examples that I'm not going to explain today, but they are also kind of popular, the lowest CMEX ones. And recently, we have also been seeing a rise in machine learning algorithms, such as neural networks. Then we have the model-independent reconstructions. This approach to a reconstruction basically take like an advantage of both the non-parametric and the parametric ones. They have a functional form. This means they have parameters that need to be inferred by data, but the functional form, it's really not important because it's really free. It has a lot of freedom of shape, so but you can use it to perform model selection because you have parameters to infer. Some examples of these reconstructions are the Beans reconstruction, the spline reconstruction, the Fourier series, for example. A Taylor series can also be another example, or you can use like a Padé approximant. And I'm going to explain two of these later in the talk, since we are working with them. So what reconstructions we use in this work? First, we have a parameterization called the graduated dark energy. This one is physically motivated. We have a dark energy density that is allowed to change sign. So we can, around certain scale factor or redshift, we can see a behavior, a weird behavior where our dark energy density can change sign to from a positive to a negative one. This is the functional form, and the parameters to infer are the sigma and the lambda you can see here. Then we have the nodal reconstruction. This one is a model independent one. Uh, Basically, how this works is we have a bunch of nodes. For example, here we have 4 nodes in this graph right here. And then these nodes are interpolated with either straight lines or a spline cubic reconstruction, a spline cubic interpolation. Here we have the two examples. For example, let's say the height of the second node can vary. We have depending on the position of this node, we will have different shapes for our function. And if we use a spline cubic interpolation, such as this part right here, you can see that it introduces noise or unwanted behavior because of the correlation between the nodes and the interpolation type we are using here. So in this work, we will mainly focus on the straight line interpolation. We also have the beans reconstruction. This one is also a model independent one. And in this type of reconstruction, we use a bunch of step functions. They are also called beans, and they are joined with hyperbolic tangents. This is the functional form, and the parameters to reconstruct are to infer are the W's. The Z's right here are the positions in the redshift, and this parameter right here is like a smoothness parameter. It controls how smooth is the transition from one step function to the other. For example, here we have a visual representation of these two types of model independent reconstructions. Let's say we have 8 parameters. They can be nodes or beans. And if we use a linear interpolation, we will have the green line. If we have a beans function, we will have either the blue one or the orange one, depending on the value of the smoothness parameter. We will mainly have a smoothness parameter of 0.15, so it will look kind of like the orange one. Then after performing the reconstructions, we do a procedure called the principal component analysis. This also named PCA. When using PCA, we can eliminate noise from our reconstruction, so we can see where is the noisy part of our reconstruction. We can see what we have to do to make our reconstruction to perform better in the future, and we can see which parts of the reconstructions are, let's say, better constrained. Here we have a visual representation on how PCA works. For example, here we have 2 PCs. We have two axes, and if we eliminate one of the principal component, we basically reduce the noise. We are losing information, but we are recovering a better dynamic behavior of our reconstruction. And here is an application for a photograph. You can eliminate 876 of the principal components of this photo, and you recover a photo that it has less weight, but it's less detailed. Next, we have an IDE model. We also reconstructed the interaction kernel. IDE stands for interacting dark energy. This means that we have an interaction between the dark energy and the dark matter. It's represented by this Q right here, but we are reconstructing the letter pi right here. This is basically the same as this one, but it's the dimensionless, so we can use it to numerically solve the differential equations here, and then we can recover the dark matter and the dark energy densities. Then we will have Friedman equation in this manner right here. When using the Gauss, the IDE reconstruction, the IDE model, the interaction kernel, we will reconstruct it using a Gaussian process, but it will be different than the usual way it's used, where we use directly to the data. We will use it uh, as an interpolation between nodes. So in a similar way to the other graph I showed you, here we have a comparison between the beans, also the blue and orange ones, and the green line. In this case, it's not an interpolation with spline cubic or straight lines. We are using here a Gaussian process to perform the interpolation. To infer the value of the parameters, we use Bayesian statistics. I'm not going to explain all of the theory here, but you can check our review in the topic here in this archive. And mainly, we will use an algorithm called nested sampling. This algorithm it's used to do parameter inference, but as a plus, it gives us also the Bayesian evidence or an approximation to the Bayesian evidence, so we can do model comparison between our reconstructions and ΛCDM. The data used for this work is basically the cosmic parameters dataset. We also use the Pantheon's full catalog of type 1a supernovae. We also use BAO low redshift data, and we also use Lyman alpha high redshift data. If you want a full explanation, please refer to this archive right here. We explain here in more detail the data used and also the code used. We have our own parameter inference code. It's called Simple MC. You can find it here in this GitHub right here. So what are our results so far? For our graduated dark energy model, we find a bimodal value for our parameters, specifically for the H naught parameter. So this is like a consequence for the possibility of allowing the dark energy density to have negative values. They all of our reconstructions with different values for lambda have a transition to a negative value around a redshift of 2.2. These right here are the functional posteriors. We have the density. You can see that at 2.2 or 2.3, we find a transition from a positive dark energy density to a negative dark energy density. This also affects the Hubble parameter in this manner, allowing it to better fit the data of the Lyman alpha Hubble parameter. Next, I present the results for the beans and nodes reconstructions, model-independent reconstructions. These ones are for the equation of state. As you can see, as we add more parameters, the structure becomes more complex, but it also presents some similar behaviors. The top ones are using the beans, and the lower ones are using the linear interpolation. And you can see that the structure is basically the same. Doesn't matter if we use either a beans or straight lines for the interpolation. We also have some interesting features, such as a crossing of the phantom divide line, in both cases. And we also have this this interesting behavior of a transition in a quantum-like behavior. These right here are the reconstructions for the dark energy density. We see also the same. As more parameters are used, the structure becomes more complex, and we see in all of them a possible transition from a positive dark energy in 0.7 to either a null value or a possibility of having a negative dark energy density, which is the same as our graduated dark energy. This right here is the same reconstruction, but using 20 parameters instead of only 6. Sorry. Using 20 parameters, and we recover an interesting behavior when checking the dark energy density. We have this is the equation of state inferred from this equation right here, and we can see a transition from a discontinuity in a redshift of 2 this discontinuity here is necessary if you want to have a negative dark energy density. Well, a transition from a positive to a negative dark energy density. When using PCA, we find that all the information beyond 1.5 in redshift it could be attributed to noise, and basically the majority of our data right here is supernovae or the Lyman alpha BAO, and as we know, the Lyman alpha BAO is pretty noisy or has a lot of systematic errors, so we have to be very careful when making conclusions about our reconstructions beyond this point. To summarize the results, basically we find some oscillations. We find that dynamic behavior is present in all of the reconstructions. The equation of state reconstructions present a quantum-like behavior. And we also have a possible null or negative values for our dark energy density beyond a certain redshift. Here we have a graph comparing comparing the fitness and the bias factor of our reconstructions. We have, as we augment the number of parameters, we see that we have logically a better fitness to the data, but a worse bias factor. But when reconstructing directly the dark energy density, we observe an interesting feature, which is that we have a positive bias factor for two of the reconstructions, but it's a really low positive, so it's evidence in favor, but it's inconclusive at best. So we need to be very careful about what we conclude with our reconstructions. And finally, when using the IDE model, the interacting dark energy model, we find a similar behavior, basically the same. We have a discontinuity in the equation of state, which means that we have a possible null or negative dark energy density. We also find that our interaction kernel can have oscillatory features. So this means that the flux of energy and matter can change in time. So finally, to summarize our conclusions, we have dynamic behavior, we have quantum-like dark energy for the equation of state, we have a possible either null or negative value for the dark energy density, but we have Bayesian evidence in favor of lambda CDM. And when using a completely different approach, which is the interactive dark energy, we have similar features. So it's pretty good evidence for our sign switching. So that will be all from my end. I hope to see you all in the Q&A session. Thank you.